to tomorrow, 5:27. Again, in class, 2:10 to 3:10 p.m. Plus 15 minutes upload time. So submit work by 3:25 p.m. Unless, of course, you have an accommodation, and I think I'm aware of everybody that has an accommodation. And of course, those of you who took the makeup exam last time, I've spoken with some of you. I'll confirm with the rest of you tonight that you'll take the makeup exam at the same time as last time. Okay. So, right. I hope you saw my announcement on Canvas earlier today, saying that we would have time to go over the homework problems from chapter 4. Rather, I will take any questions about the homework problems from chapter 4. And of course, tomorrow in the initial segment of class, we will go over as much of the review, the practice exams, as you like. Hopefully also, okay, so Keenan asked for 4.4.
Yeah.
Good. All right, so what does 4.4 say? .4 asks, what is the symmetry group of a parallelogram which is neither a rectangle nor a rhombus. Okay, what's a rhombus?
4 equal sides.
Yeah, it's a diamond, basically, right? So, a rhombus is a quadrilateral with 4 equal sides and 2 pairs of congruent angles. And 2 pairs of...
Well, that's not specific to a rhombus, is it? That's just about parallelograms.
Yeah. So a rhombus is a parallelogram, right? Yeah. Okay. 2 pairs of congruent angles, i.e. a parallelogram. So a parallelogram with 4 equal sides, right? Okay, so what is the typical quadrilateral that we're describing here? Neither a rectangle nor a rhombus. So in other words, the internal angles are not 90 degrees, and the sides are not all equal, right? So here's a typical example of a parallelogram which is neither a rectangle nor a rhombus. Okay? So, what symmetries does this have? start at the smallest dimension. Does it have any points of symmetry? Does it have any lines of symmetry? Does it have any symmetries in general?
It has a point of symmetry.
It has a point of symmetry, yeah, which is the center of this figure, right? P. So has a point of symmetry. That is to say, when we do a half turn through P, this parallelogram is fixed. Right? Yeah, good. Jordan said exactly that. I just didn't look quickly enough. Good. So, are there any other symmetries of
Other than the identity.
other than the identity? Good. Right? Remember, the identity is always a symmetry. We stated that last time, that the symmetries of a set always form a group. Therefore, the identity must always be a symmetry. Or you could just look at the definition of identity and then it fixes everything. So it must be a symmetry, an isometry of any set. Right? Okay, so sigma sub p is a symmetry. And in fact is the only symmetry. Okay, so in other words, the group of symmetries, a group of symmetries of our figure is the group generated by sigma sub p. Okay, so what do we know about half turns? What's the order of any half turn? 2, yeah, all half turns are involutions, right? So we call this C2, the cyclic group of order 2. So Ryan asked, what makes that a point of symmetry? Well, take this point P and take any point Q on our parallelogram. Then we have sigma sub P of Q is on the parallelogram. Namely, it comes over here, right? So a point of symmetry is a point about which a half turn fixes our figure. Okay, that's the definition of a point of symmetry. And you can verify for yourself visually that when we take, say, this has coordinates x comma y, you can verify analytically, if you like, that this will...
P is the origin.
Yeah, sorry. So let's assume P is the origin there. That's a good point. Thank you. Right. If I were to, and of course, I could just translate to the origin, but it's important to say that in order to make this formula valid. Good. Okay, so so Keenan asked, does that mean that for a point of symmetry, any point on the parallelogram's half turn is just its prime? So sigma sub p of q equals q prime. Yeah, that's I think what you're saying is.
So I think that's fixing it point-wise.
Well, we have true. So I think. I'm sorry. I interrupted you guys. What were you saying?
It requires. Is that how it works? How's that notation works? Prime just means it's image, right?
Yeah. I think that's what Keenan is saying here, we can just name this point Q prime, right? Yeah, sorry, I was reading the notation. Sorry if that was confusing. So that's basically a notational aspect of the situation. Is that okay, Keenan? Cool, great. Okay, so the second part of 4.4 asks, what is the symmetry group of a rhombus that is not a square? Okay. So let's just take some rhombus. Pretend these are all the same length. What are the isometries that fix this figure? Let's say the center is P. Or if we like, let's just say that it's centered at the origin. So what isometries fix this figure? Say that again.
Sigma O.
Sigma O. Yeah, that's just what we had here, right? I named PO. So here I'm streamlining things a little bit. Okay, so sigma O is an isometry. I should mention yielding point of symmetry, the origin. What else do we have?
Reflection over the lines bisecting each of the angles.
Yeah, and Thomas also says the same, just adding some coordinate axes in here, just to make it easier to describe, right? So if this is the origin, let's just say we have the x-axis and the y-axis, then sigma sub v and sigma sub h are familiar notation for reflection about the x-axis and y-axis respectively, are also isometries. Is there anything else? Sorry?
I don't know, but nothing else. It's not trivial.
Yeah, right. So in fact, this is a familiar situation to us. It's just like a rectangle, right? So rhombus that is not a square has symmetry group well, why don't I just write it out just so we hopefully get a little more comfortable with this notation. Okay, I recognize these three symmetries. I take the group generated by these, and I get V4. Okay.
Just the same as a rectangle, even though it's not a rectangle.
Yeah, right. So this tells us something, right? I kind of brought up this program of Felix Klein where you can study an object by studying its group of symmetries. So, sorry?
It has to miss things then.
Yeah, exactly. So this kind of gives us a glimpse that by studying symmetry groups, we lose some information, but somehow there are salient features captured by the symmetry group. Okay? So let me ask you this. Why is it so important to include this clause in both the first and second parts of this question that we're not dealing with the square.
It would have two more lines of
Have
symmetry
rotational symmetries in two.
and.
Yep, it would have a couple more lines of symmetry and it would have rotational symmetry.
Other than the half turn.
Sorry?
Other than the half turn.
Other than the half turn, right? It would have
Quarter.
a rotation by 90 degrees, right? So a square also has a rotation by 90 degrees
Never cubed.
as a generator,
Yeah.
right? As a generator for a symmetry group. So its order is more than 4. Okay? So this is where we're headed next week, or maybe at the beginning of the week after next. We'll talk about a symmetry group of a regular polygon, such as a square.
Okay. Rotations.
Yeah, we'll do rotations first, and then we'll come up with some analytic formula for rotations as well. Okay? Good. Okay. More chapter 4 questions. Do we have it? Oh, yes. Yeah, so Jordan asked we go over 4.1. I just wanted to say this note. Cn is the cyclic group of order n. Okay, just in case that comes up, which if you continue to study group theory, it definitely will. This is standard notation. Okay. So, right, so 4.1 asks us to prove that if alpha is in the group generated by half turns, then alpha is an isometry. Okay, so first of all, there are two cases, right? The group generated by half turns contains two types of transformations. Who can tell me what they are?
And translations.
Half turns and translations, right? Because we had this whole theorem about how any translation can be expressed as a product of two half turns, and how the product of two half turns is always a translation, right? Okay, so two cases. One, alpha is translation. Well, I think we already proved that translations are isometries, right? But if not, you can do it totally analytically.
Distance formula.
Yeah, by using the distance formula and just assigning some variables to the translation vector of alpha, right? A comma B. So let's just write that out, okay? So with translation vector, A comma B. Actually, that's kind of unfortunate. Let me,
Wait, what happened?
this is my notation, this is what I have written. I don't want to screw myself up. I do that enough. Let's just say it has translation vector E and F. Okay, so if I really wanted to carry this calculation through all the way, I would take points P and Q, and compute the length of the line segment between P and Q, right? Which is just C minus A squared plus D minus B squared, square root of all that. And the length of the line segment alpha P, alpha Q, which is just equal to the square root of, so I operate alpha on P. What does that give me? I get A plus E, comma, B plus F for P. And then I get C plus E, comma, D plus F for alpha of Q. Okay, so in other words, I get C plus E minus A plus E squared plus D plus F minus B plus F squared. Sorry, got a little cramped over here. But hopefully you can see that these are equal, right? My E's cancel here, my F's cancel here, and I just get the square root of C minus A squared plus the D minus B squared. Okay, so therefore distance is preserved. We have an isometry if alpha is a translation. Now, what about the case where alpha is a half term, right? Because we know that anything in script H has to be one of those two things. Okay? Well, it's exactly the same, but of course we have a different formula, a different equation for what a half term is, right? So, case 2, alpha a half term. So let's say alpha is equal to sigma sub r for what notation did I use here? R is the point x comma y. Okay. Then you do the same thing as we did here. We have the value of the distance between P and Q, and then just operate.
At least it's slightly more interesting because you get to use the fact that negative 1 squared doesn't change the value.
Yeah, right. So I'll write that down. Just, I mean, if you're really not interested, then is this okay with everybody? Does this feel fine? I don't want to necessarily. Yes. So Jordan asks, we just have to show distance is preserved to show that a transformation is an isometry.
So that's a definition of an isometry, right?
Yeah, that's the definition of isometry. Of course, isometries have a lot of other nice properties, but that's the definition, which in fact is not so hard to check, right? It's don't be fooled by the long list of properties that isometries have. Those are nice things that we can use. To verify that something's an isometry, we just have to show that it preserves distances. Okay? Okay. Good. So, everybody okay with 4.1? Okay. Further questions?
For 4.3, would you recommend doing it analytically? Using the formula?
Yeah, I would say,
Because like the last example was it got complicated using the formula.
yeah, and I still think that's the best way to go.
Okay.
Yeah. So for those of you who didn't hear the question, for question 4.3, the last row of that table results in some non-trivial system of two linear equations that you have to solve for x and y. So maybe we should just do that together. Okay, so question 4.3 asks you to fill in this table. Okay, and we're just going to look at the last row. So we have equation of line M is y equals 2x. And we have point P. This is what we want to fill in. Okay, and we have here the point sigma sub m of P, and they give us this value, 4,3. Okay, so our job is to fill in star here. Okay, so how do we go about doing this?
Formula.
Well, one way to proceed, which in this case I think is the way I would choose, is to just use. So Jordan asks, can we also solve this graphically using triangles? And the answer is yes. You certainly can do that.
Okay, sorry.
Sorry?
Right now, because something less tedious, at least.
Yeah. But it's still well justified. Okay, so okay, so what is Keenan saying here? So we know the equations for x prime and y prime, and the equations. So find a, b, and c for the equation and plug in the values of the half term. Yeah, right. So we have the equation of a line here, right? This is negative 2x plus y plus 0 equals 0, right? So this is a, b equals 1, c equals 0, right? And what's the equation for our reflection? Well, it's this terrible looking thing, x minus 2a ax plus by plus c all over a squared plus b squared, comma, y minus 2b ax plus by plus c all over a squared plus b squared. That's my ordered pair, right? And I set this equal to the point they give me, 3, 4.
4,3.
4, 3, yeah. Okay, so I'm just going to plug in a equals negative 2, b equals 1, and c equals 0 into all these. And then I get a system of two linear equations in two unknowns, and I can resolve that. Okay, so don't despair. You know, this isn't the point of this class. Feel free on an exam to use a linear equation calculator solver if you want. That's fine. Some people get some sick satisfaction from actually solving these systems of equations, which I wouldn't fault you for. But you're not required to do that. Okay? As long as you get the core idea.
At least you only have to do most calculations once because they're almost identical.
Yeah. So, and this really doesn't reduce, it reduces not so horribly.
They're all fractions of 5 though.
Okay, so, how do we feel about that? Okay? All right. So, any further questions about chapter 4? One more. Okay, so let me just remind you that we were in the midst of talking about expressing isometries in general as products of reflections, right? So we finished yesterday with the following result. Here, and isometry that fixes exactly one point is the product of two reflections. Okay, now if you will recall what we did last time, we started out with the most restrictions, right? We said, what if an isometry fixes three non-collinear points? Then we, and we deduced that that must be the identity. Then we discussed if an isometry fixes 2 points, then we must have that it is a reflection or the identity, right? And now we've relaxed ourselves even further in saying that an isometry that fixes 1 point is a product of two reflections. Okay, so now, so here's a corollary of this. An isometry that fixes a point is a product of, at most, two reflections. That's just combining the theorem that we proved just before this and this theorem. Okay? Okay.
Oh, instead of exactly 1 point.
Yeah, right. We're just saying that it fixes a point. We don't know if it fixes any other points. Okay? So, then, the reason I state this way is because this will be our stepping stone to proving our main theorem. Onto the main theorem. So, let me just say this. Every isometry is a product of, at most, 3 reflections. Okay? So, okay, so firstly, let's look at the identity, right? So, iota sigma m for any line m, right? Any line m. Okay, so our main isometry, a very important but boring isometry, satisfies our theorem. Right? Okay. So suppose alpha not equal to iota is an isometry. Well, since it's not iota, we know that it does not fix at least one point. There's a point which is not fixed by alpha. Right? So we'll say with alpha of p equal to q, p not equal to q. Some points. So let's set the line m to be the perpendicular bisector of the line segment PQ. Right? Then what we have is sigma sub m of alpha of p is equal to sigma sub m of q, right? And by our choice of m, the definition of sigma m gives us p back for this, right? By definition of sigma m. Okay. So then, by the last corollary, sigma m alpha equals beta, where beta is the product of at most two reflections. Right? That was our last corollary. Okay. So now we're basically done. Okay? Because I can multiply both sides of this by sigma m, which is the inverse of sigma. Right? A reflection being an involution. Okay. So this implies that alpha is equal to sigma m beta is at most three reflections. Okay, so that's kind of nice. But it's not that nice. It's not constructive in any way. Given an arbitrary isometry, how do we write down the reflections that it can be factored into?
They're unique.
Well, that's a good question.
I feel like they should be, but.
Well, let's go through the proof where we explicitly construct them and see if we can tell if they're unique or not. Okay, but before we do that, I just want to make a remark here. So, we've proven that reflections generate I, the group of all isometries. Right? In fact, we said something stronger. Right? It's not just that an isometry is a sum product of reflections, it's at most 3. Okay? So, right. So in general, we would like to know which reflections and isometry is a product. So, just given an arbitrary isometry, it's hard to say. We have to have a little more information. Okay? So, and that information is we must know the image of some isometry of 3 non-collinear points. Okay? So, it's really warm in here. I'm just going to take a water break. I'll be right back.
So it's the same logic as like.
Proving they're equal to 3 points. But it's enough unique later than
It's much related to that, yeah.
I should have water today. I already have actual air that works, it is turned on. See those?
Sorry. Just, I think I might change my wardrobe. Some short sleeve shirts or something. Okay, so, so we need more. To tell this, we need more. Specifically, to factor an isometry alpha into reflections. We need to know the image under alpha of 3 non-collinear points. Okay. So, theorem. And then we will make a long string of computations that might seem quite confusing. But then afterward, we'll draw a picture to see what's actually going on. Okay? So, and the reason I choose to do it that way is because if I just showed you the picture, it's a little bit overwhelming. It's hard to tell. So once we do the computation together, then we'll take it step by step and show what we're reflecting where. Okay? So, if the triangle PQR is congruent to the triangle ABC, and of course, when you went back and read section 1.2, hopefully you recall what this means. For triangles to be congruent, it means that all their side lengths, their corresponding side lengths are equal. That is to say, the distance from P to Q is the same as distance from A to B. The distance from Q to R is the same distance as B to C, and the distance from R to P is the same as the distance from C to A, and all the angles measure the same.
The holistic geometric proof methods.
Right, so, of course you don't have to check each one of those things, right? This is where you get your side angle side, etc., which was discussed in section 1.2. But, so, just want to make sure we're all together on this. This is notation from section 1.2. Okay? Then there is a unique isometry. Alpha. Such that alpha of P equals A, alpha of Q equals B, and alpha of R equals C. Sorry. Yeah, that's right. I wrote the wrong thing in my notes, but this is correct. Okay. So bear with me here. I know this will seem possibly like we don't know what's going on. I'm just going to say it and then draw it. Okay? So, what we have by congruence is the first, this is what we'll use, that AB is equal to PQ, AC is equal to PR, and BC is equal to QR by congruence. Okay, so first, if A is not equal to P, set alpha 1 equal to sigma sub L, where L is the perpendicular bisector we'll call that PB because I'm going to say that phrase a bunch. We'll just call it perpendicular bisector of PB. Okay? Of the line segment PA. okay? And if, if P happens to equal A, then we just set alpha 1 equal to the identity. Either way, we have alpha 1 of P is equal to A. And let alpha 1 of Q be equal to Q1, and alpha 1 of R be equal to R1. Okay, so maybe you can kind of see where this is going. We're going to do the same thing for each.
Making sure to preserve our previous ones.
Right, so we have to construct alpha 2 such that it works well with alpha 1. Okay, okay, so let's do that. So we'll start the same way. If Q is not equal to B, if Q1 is not equal to B, then let alpha 2 be equal to sigma sub m, where m is the perpendicular bisector of the line segment Q1B, right? And similarly, well, I guess I should say, then we know that A lies on the line M since the distance from A to B is equal to the distance from P to Q is equal to the distance from A to Q1. Okay? Good. I should say, since we have isometry and A is in the set of points equidistant from B and Q1. Right? That's why A must be on the line M. Okay? Okay. And then similarly, we have the case if Q1 happens to equal B, then set alpha 2 equal to the identity. Okay? And either way, if Q1 is not equal to B or Q1 is equal to B, we have A2 of A A lies on M, and if alpha 2 is sigma sub M, then A must be fixed by alpha 2, and of course, if alpha 2 is the identity, then we get alpha 2 of A is equal to A. Okay? And of course, alpha 2 of Q1 is equal to B in either of these cases. Right? Okay. So, you probably guess at least the general form of what we're going to do next. Right? We'll have to incorporate the value of the image of R under A2, and then construct an alpha 3. Sorry, not A2, alpha 2. Okay, so let alpha 2 of R1, remember, R1 is the image of R under alpha 1, okay, equal R2. Then we say if R2 is not equal to the point C, then let alpha 3 be equal to sigma sub n, where n is the perpendicular bisector of the line segment R2C. So in this case, we have n is equal to the unique line through A and B, right? Since again, we have this string of equality of distances due to the similarity, the congruence of the triangles. That is to say, remember, isometries preserve triangles, right? Okay. Okay, so, and of course, this is what tells you that A is on that line N, and similarly, we have BC equals QR equals Q1 R1 is equal to B R2. Okay? So, and then of course we have the case if R2 equals C, then we let alpha 3 be the identity. In either case, we get alpha 3 of A is equal to A, right? Because A lies on this line N, or alpha 3 is the identity. Alpha 3 of B equals B, and alpha 3 of R2 equals C. Okay, so what do we do now? We're trying to construct this unique isometry that we can
propagation.
In what order, right?
A through A2.
A3, alpha 3, alpha 2, alpha 1, right? Okay. Okay, so we set alpha equal to alpha 3, alpha 2, alpha 1. Then we see alpha p is equal to alpha 3, alpha 2, alpha 1 of p is equal to alpha 3, alpha 2 of A, right? Which is alpha 3 of A, which is just A. Alpha Q is alpha 3, alpha 2, alpha 1 of Q, which is alpha 3, alpha 2 of Q1, which is alpha 3 of B, which is equal to B. And alpha R. We make a similar computation to get alpha 3, alpha 2 of R1, which is equal to alpha 3 of R2, which is equal to C. Okay, so this is unique because, remember, an isometry is determined by 3 non-collinear points. Okay, so that's admittedly somewhat confusing without a picture. So let's draw a picture. Okay, so pictorially, we'll take some triangle. P, Q, R, and I'm going to pick all unique points, right? So the picture I'm going to draw has legitimately 3 reflections, is the isometry that will take PQR to ABC. Okay, so that is, I want to come to this point A, R1, Q1, L, the perpendicular bisector of line segment PA, right? Okay, and then I'm going to reflect this onto R2, B, here's my line M, the perpendicular bisector of the line segment BQ1, right? And finally, I draw this line N, and I take C up here, and the perpendicular bisector of the line segment R2C. Okay, so maybe just a little color to emphasize where we end up. We get to this congruent triangle to PQR. Okay, so we construct these three lines, L, M, and N, as perpendicular bisectors to arrange all 3 points, P, Q, and R, onto A, B, and C. Okay, so the takeaway is, once we know that, once we know the image of 3 non-collinear points of an isometry, we can construct all these perpendicular bisectors. And those are the reflections that comprise our isometry. Okay? Okay. So, here's just a quick corollary that's basically just a way of viewing the concept of congruence classically in terms of transformation geometry. Okay? So, let me say, corollary. To segments to angles or to triangles are congruent if and only if there is an isometry taking one to the other. So why do I bother saying this? Well, it's because technically, when you do elementary geometry, the notion of congruence for 2 line segments is different from the notion of congruence for 2 angles, is different than the notion of congruence for 2 triangles. But now, we can make a generalized definition of what congruent means. It just means that one geometric figure is taken to another by an isometry. Okay? So, okay. So, section 5.2 in the textbook is primarily about paper folding experiments. Okay, now if we were in a usual classroom setting, I would pass paper out and we would actually draw on the paper and do some folding experiments, and then you would make some conjectures. That doesn't exactly make sense for us to do right now. So what I'm going to do instead is homework for extra credit. I'll ask you to do these paper folding experiments at home over the weekend and take some pictures and send them to me. And if you bother to do that, I'll give you 2 extra points on an exam. Okay? Maybe it's worth it, maybe it's not. I think you should read the book for this section anyway, but if you read it, then I think you'll find it hard to not do the paper folding experiments, okay? So, I'll ask you to read section 5.2, pages 36 through 39. And I want you to identify the 3 paper folding experiments proposed by Professor Martin, the author. Carry them out. That is, carry out the experiments. And send pictures of your work for +2 points. To your exam score. That is your total exam score, right? At the end of the term, in a couple weeks from now.
So the non-final exam score.
Yeah, right. To your midterm exam score. Okay? And these are fun. These are fun things to do. But you don't have to do them. But I would strongly recommend it. I wish that we could do this together now, but it just really doesn't make sense for me to be like, okay, everybody get out paper. And then turn your cameras on and show us all your work. That's just not the way it's going to be. Soon though, right? We have to turn the corner. Okay. So, the latter half of section 5.2 gives us the first rudimentary or synthetic definitions of what a rotation is. Okay, we've been a little bit fast and loose about what rotations are, right? Because we have a good intuition for what they do in the plane. But now we're going to start to lay the groundwork to explore them more analytically. Okay? So, oh, and by 6-1. Remember, we don't have class next Monday either. It's Labor Day. So just
Memorial Day.
Memorial Day. Yeah, sorry, I always confuse those. Left and right. Memorial Day, Labor Day. So yeah, just email me by Tuesday if you want to do this. Okay. So, definition. A rotation about a point C through a directed angle theta, and this O with a strike through it is Greek capital theta, degrees, I guess we'll say, is the transformation denoted rho sub c comma theta that fixes we have rho sub c comma theta of p is equal to p prime. So that the distance from C to P is equal to the distance from C to P prime. And theta is the angle measure from the ray CP to the ray CP prime. Okay, so again, throwing some terminology at you from section 1.2. Right? 2 points specify a ray as well. So C is the terminus, and P lies on the half line that originates from C. And so, I mean, you know, I'm saying a lot here. I'm using a lot of words without really saying that much, right? So I have P prime, and theta. This is a very familiar situation, right? We've all taken calculus and done a fair amount of trigonometry along the way, so we're just saying this basic thing. Okay? Okay, so just a couple notes here. We'll say convention dictates that rho sub c comma 0 is equal to iota. Right? If you fix c and rotate by 0 degrees, you haven't done anything. You've just left everything fixed. Okay? And we also say rotation rho sub c comma theta has center theta. Center c and directed angle theta. Okay. Here's an unsurprising theorem. Rho sub c comma theta is an isometry. I have full confidence in you. You can prove this. Okay? And if you get stuck, the proof is written in the book. But just take a couple minutes and think about this. I believe in you. I know you can do this. Okay, so now I'm going to introduce some notation that, again, I really don't like. It's kind of thematic. I think you've heard me say that a lot at this point. But again, the textbook uses it, so just continue to use it. P, the circle with center C, and radius, the distance from C to P, is denoted C sub capital P. I hate this. I hate this. Okay? I was just saying, C sub n, lowercase n, is a cyclic group of order n. C sub capital P, if C is our center point. Yeah, this is terrible, but
Oh no.
yeah. But the dead giveaway is that the subscript is capital.
Why couldn't they just do a circle with a C P like they did in the shape?
The primitive days of 1992 didn't allow that in LaTeX. No, I don't know. I don't have a good answer for that. I'm sorry. Oh, I'm sorry. Radius,
Yeah.
the length from C to P. This is to say that the segment from C to P is a radius, right? That is to say, we have our point C and circle. Here's P. So this length is the radius, is the length of the radius, and this segment is a instance of the radius. Okay? So Thomas asks, can you change it? Can we say
It's so bad.
it's really bad. It is really bad. So why don't we say why don't we just say center Q? Right? Because it's just the name of a point. It seems superfluous to me to use C. Okay? So why don't we just change this to Q everywhere?
Honestly, how bad this notation is, you want to specify you're trying to circle everything using anyway.
Yeah.
Variable names.
So we'll just have to see how it plays out. If I know that confusion is going to arise, don't worry. I'll try to make a point of saying explicitly what's going on. Okay. So here's a theorem. A non-identity rotation fixes exactly one point its center. Rho sub C theta fixes all circles with center C, regardless of their radius. Okay. Furthermore, if C a point and we have theta and phi we have a couple identities which just encode what you already know about how angles work. Then we have rho sub c comma theta composed with rho sub c comma phi is equal to rho sub c comma theta plus phi. And also we have a formula for the inverse of c sub theta. Would be rho sub c comma negative theta. Okay? Furthermore, the rotations with center C form an abelian group. The involuntary rotations are just half turns. And furthermore, rho sub c comma 180 is just sigma sub c. Okay? We already knew that. That's just new notation, right? So these are all the nice facts about rotations that once we get to the point where we have an analytic expression, we'll come back and prove these things. Okay? I just wanted to tell you all the nice things about these transformations now, and we'll come back to that probably at the end of next week. Okay? All right. So, with that, we can move on to chapter 6. Okay, so we know translations are isometries, and I've told you now that rotations are isometries. We'll come back to that, but you can take my word for it for now. So we want to take a closer look at the product of two reflections and say how that relates, how isometries of that form relate to translations and rotations. Okay. Okay, so let's take a closer look at isometries which are the product of exactly Well, first of all, every reflection is involutive, right? So when I say we'll look at isometries that are products of two reflections, we'll take those reflections to have distinct lines of symmetry. Okay? Assume that L, the line L, is not equal to M, and we'll study sigma L, sigma M. Okay. In order to carry out this study, there are two cases, right? What are those cases? We're assuming L is some line which is not equal to M.
They are parallel.
Yeah, either M and L are parallel or they're not parallel. They intersect somewhere. Okay? There are two cases. One, L is parallel to M, or two, L and M intersect. So, okay, so let's assume first that L is parallel to M. So here's a definition. With L parallel to M, let the line LM be the common perpendicular to L and M. Directed distance between lines. Okay. We call the directed distance from L to M the distance Lm. Okay. Pictorially, we have, let's say this is L, and this is the line M. We have a common perpendicular since they're parallel, and we'll call this point of intersection L, and this point of intersection M. Then this line is the unique line through L and M. Okay, and then the distance LM is the directed distance from L to M. Okay, so directed distance is a characteristic that two parallel lines share. Okay, it's kind of a way of telling the distance between two lines. But
Shortest distance possible.
yeah, so this is the definition of, yeah,
Right, okay.
yeah. Okay.
I was like, there's no direction on this distance,
No, yeah, it's that's completely correct.
because it's a specific path that has to follow more than distance. So it's directed.
Right.
Okay.
Okay. So, I'll tell you this theorem, and then I assume that tomorrow we'll spend all our time before the exam talking about some of the practice questions. So we'll prove this theorem next Tuesday. And then, yeah, I'll just state it. There's no point in trying to prove it in 3 minutes, yeah. If lines L and M are parallel, then sigma M, sigma L is the translation through twice the directed distance from L to M. Okay, so this is our first handle on an explicit description of what the isometries that are products of two reflections look like. Okay, of course, this is in the special case where L and M are parallel. Okay, so we'll prove that on Tuesday. And this actually has a lot of consequences that we will explore. Okay, so don't forget office hours tonight, or this afternoon I should say, 4:30 to 6, and also tomorrow morning, 10 to 11:30. And yeah, good luck on the exam tomorrow. I'll see you all tomorrow.